Marek.
Oh, thank you very much, and thank you for invitation. I am sorry that I couldn't be with you personally, but I am with my soul, with my body and everything, and I am like in Paris. So thank you that you allowed me to speak online. Yeah.
Yes, but we will maybe meet this in some months.
Yeah, fantastic.
I'm waiting for Volodya Rupsov.
Oni tam też kontrolują, nie nagrywają później, to oni tam ktoś jest technik jakiś, który... Także...
Okay, Marek.
Oh, merci beaucoup.
So, dear Marek, we will begin with Marek Bozejko, deformation and q-convolutions, old and new results.
Yeah. So merci beaucoup, Gerard and Carol and all participants. And I am happy that I am with you with our mathematics and physics. And that talk will be related to that function that is density of q-Gaussian measure. And there is a lot of combinatorics around this. And that physics, of course, because when q is equal 1, this will be classical Gauss measure and combinatoric of Hermite polynomials. But in more general will be more general. And my plan of my talk is following. First, I start with QCC relation or CRI relation. Also for q bigger, before we did for q less than 1. Combinatorics, how it is here. So, and main topics on my talk will be related to new class of Hermite polynomials, q-Discrete. That is well known among people in let's say, combinatorics and orthogonal polynomials, but I don't saw so much paper in physics or mathematical physics related to this. So, of course, this will be also interesting. By the way, the Gaussian measure in that case will be discrete measure, so and connected with so-called Jackson measure. So measure which is supported on geometrical progression depending on Q. If I have time, I speak a little bit about analog and connection with convolution, Carnovole and Koornwinder, like special case Boolean convolution we discover in Wrocław and classical. I will not said so much about braided Hop because my time is rather big, but nevertheless, I would like more spend time with construction of q-Discrete Fock space, that is new space, and also q-Discrete Brownian motion and corresponding q-Discrete Hermite polynomials of type 1. Also, there are type 2, but this will be corresponding to the complex plane. And maybe if I have time, I will say something matrix version or Khintchine inequalities, which are important to study for Neumann algebra generated by the new Gauss. So this is my plan. As you know, I usually have plan for 2-3 lectures, but I be starting to do this. So main things when we discovered with Roland Speicher some years ago, that will be q-Gaussian, and corresponding for that orthogonal polynomials, there are q-Hermite, which were discovered many years ago. But the measure, orthogonalizing measure, is θ1 function of Jacobi, which explicitly is written density. This is here 1 over pi square root 1 minus cosinus theta and some product when 2 cosinus is x square root of 1. And support of that measure, as you see here on the picture, is bounded only for q equal 1. This measure is Gauss, classical Gauss. But for q equals 0, this corresponds for so-called Wigner measure with Gaussian measure in free probability. For q equal -1, this is two peaks. This is the Bernoulli or Fermi statistics. Also, as you see from the picture, there is a such point, like a saddle point, when statistics change from bosonic to fermionic. And I think for you, for mathematical physicists and combinatorics, that point should be very important. This is about -0.1. And it's known in literature that point was discovered by many people. Anyway, but this is not main. As I see, I would like say more about combinatorics, but also this, I mentioned that. So we extended that, and then the relation here is we have creation annihilation operator, and depending not only q, but also we have yet another parameter s, which is like kind of spin, mathematical spin. I don't know what it means. And the commutation relation when s is equal 1, and q equal 1 is just classical commutation relation. This is creation annihilation operator. And S parameter S appears mathematically very naturally, because what we are doing when we are Q Fock space, that means when S equal 1, that we just make special symmetrization, just operator with chain scalar product on classical tensor, so free Fock space, we change scalar product by kind of symmetrizator. This is not only positivism is not just projection, but nevertheless this works. And main problem is proof positivity for q between 1 and -1. And we did this some years ago, and that is many results in this direction. But it's not so important. Anyway, but when we have parameter S, also, we would like extend this to the parameter when q is not between 1 -1, but q bigger. And also we are doing this with Speicher. So we start with q relation, what we did with Speicher. And now the parameter S is kind of dilation by number operators. So n on the tensor is n. And if you take such operator when AQ is just Q commutation relation, Q creation, then we obtain new, and here is the new relation which two parameter we have some, and among them with S is equal Q, we obtain q-Discrete, for example. This is something special, what we discovered some times ago. And now comes to some combinatorics. Because when you have a random variable, like here q-Gaussian, the Gaussian is just position operator, just creation plus annihilation. So in general, that we, in some state like vacuum, we obtain probability measure with all moments, and then we define it q-cumulant, and this was done by Biane and Anshelovich some times ago, in such a way that moments of just measure is just you function q to the crossings, and we work on partition of the set 1 to n, and the RMQ is just that cumulant. And main property, so this is the main combinatoric of moment cumulant formula, and that was discovered by statisticians some times ago, but now is with parameter Q or S and other where. And here, of course, when you have partition, this you can block, and then you just make product of that function, RMQ. And crossing, you just looking like here, and that was the idea done by Professor Biane from Paris, that we should draw that connection like hyperbolic. So when partition is, for example, 1, 3, 5, and 2, 4, so we take just crossing, we obtain by taking just connecting by semicircle or something like this, and this is my method of this combinatorial method. There are a lot of things around this. Also, some related things. I only say that was done by Andunika about special reducing number of crossing left or right. but this was not. This is related to the sum function C0, which will be later. And when we have cumulant, that is the well-known in classical probability that when you have two probability measure, me1, me2, that we define it new measure, just add cumulants, and that is the cumulant of the convolution. So this is usually people use Fourier transform, but this is multiplicative way, but this is additive way. That was work very good for Q0 when Professor Wojkulescu discovered free convolution. Yeah, is okay. My voice is no okay. No remark. Okay. So this is the main idea, and only problem find resonate and good cumulant function. And of course, for q equals 0, 1, -1, this is easy, but for other is some problem. And problem which is still open by Philip Biane is that q-convolution is positively preserving. I don't know, but I will be extended, but another parameter S, and we obtain new q-convolution will be corresponding to q-discrete Hermite polynomial of type 1. We give Fick formula, and our conjecture is that that will be okay. The combinatorics I show in a moment to you, and from this you can imagine that should be everything fine, but that paper is not yet finished. So some sense that project. So yeah, but I think that after that conference we can do. So how we doing this commutation relation with parameter, and that is the combinatorics formula which you obtain with Professor Yoshida from Tokyo. This is just Wick analog of Wick formula with two parameters S and Q. Our position operator Gaussian GF. This is IF creation plus A star F is annihilation. And then when you calculate generalized moment for that F function for suitable Hilbert space, that we obtain like correlation Fi, Fj, but also here appears function when S equal 1 is the Q to the crossing, but also here appears new function, combinatorics, and I don't found in many places in combinatorics that function. This is we call this inner point. Inner point just, this is summation of input between point I and j. When I and j is just E1, J1, and then that formula is explicitly sum of jk minus ak, and that is natural function. So when I say you that our q-discrete when S will be equal q, that you can see, and that is not trivial to prove this anyway, but this for you as a mathematical and physicist will be important. There is a Wick formula which you obtain a measure, and explicitly you can, in some cases, you can write down at least orthogonal polynomial, and maybe if you have chance, we obtain the orthogonalizing measure. So only maybe I recall that crossing numbers is just as I wrote for two partition. That means we have 2 point A, B, C, D, like here on the pictures, and we look for the crossings. Other function is the pair bracing of two pairing, or nowadays in nesting. So he's not looking how crossing, but each block is connected in another. This called nesting, or Andunika called this pair bracing. So you have pair A, B, C, D, and you ask when CD is included in nesting in the, and I was very surprising when sometimes ago I proved that two function, crossing, nesting, and inner point satisfy such a beautiful relation. What is nice for me that we proved that combinatorial formula using commutation relation. Of course, later when we know that we can prove combinatoric, but my question to you, because it's combinatorics people around you, what means that formula reality? Because it's crossing and nesting. So it's like two statistics, yeah? So two particles are between, and this is the reaction. Crossing is just relation. And inner point, you're looking, for example, in that case, inner point is just 1 and the second two, so it's 1 and crossing is 1 and pair bracing is 0. So this is but it's more general for any two pairings. So that means for two element set we just pairing and then looking for the and maybe even I wrote no, I don't wrote here, but I maybe later I see, yeah. Also, I use that pair bracing on nesting. That function appears when we consider q-commutation relation for q bigger than 1. And then it's just a relation like commutation relation, bf b plus g minus b plus g bf. And that's q to the number operator. And new Gauss is, of course, position plus momentum, so BF plus B star. And when you calculate moment, you obtain Q just, of course, correlation between F and J, Fi, Fj, and also the function Q to the pair bracing. So the nesting. So you see, and that is a special case when Q equal S equal 1. Yeah, this is that more or less something. And the construction is just you take Q equal 1 over Q, S equal Q, and that the operator creation annihilation is just with two parameter 1 over Q. So you put S 1 over Q, no Q and Q replaced by 1. Of course, here is the main problem is such a construction. You would like have that the construction will be self-adjoint operators. That means plus should be conjugate to yeah. Now maybe I recall what I mean q-Discrete Hermite polynomial, because here in one-dimensional case, our operator will be satisfy the relation q-Discrete. And q-Discrete relation, you know, of course, A0 is 1, A1 is x, but we have relation between that orthogonal polynomial like x hn is equal hn plus 1 plus q to n minus 1 times quantum number n, when quantum number is q to n minus 1. And this is type 1 discrete, and that discrete will be just distribution of q discrete Gaussian for q between 0 and 1. Of course, there is a type 2 in literature, discrete Hermite polynomial. This is coming to the variable to imaginary I. So that function is on the x, real, but you come to imaginary part of this. And that, I think among mathematical physics like you are here, should be the word natural, but for mathematician is just trick, yeah. To obtain explicit the definition, and we should use the just this q version of exponential function, which are two such a function, yeah. So that the one is e small eq. When you take instead factorial, you have some kind of factorial with 1 minus a, when aq factorial is 1 minus aq, a minus ak minus 1. And also big eq exponential function is when you the same, but you add q to the n over 2. N over 2 is coming from permutation group, because this is the longest element in the some says along Kelly graph or permutation graph when you use only inversion. So this is that. And of course, here is Newton symbol, also Gauss symbol, because Gauss before Newton defined that. Of course, Gauss defined that Newton symbol nj over q just for q, which is the prime numbers of power of prime, because this was connected with subspaces of linear spaces over field of q elements. But here q is just between 0 and 1. So something is like continuous Gauss symbol. I don't know, that should be some object like kind of fields which have a related q numbers. This is more or less should be quantum group. I don't know, but this will be for you. So this we use that natural, and also that function satisfies beautiful relation. So AQ, the bigger is the product, 1 minus q to the n z, and that function AQ minus z is 1, but of course that function are not additive, multiplicative but what is nice, you can find literature that q-discrete HM orthogonal polynomial have orthogonalizing measure. This is EQ squared minus q squared x squared with Jackson measure. Jackson measure I wrote here. This is just measure, let's say, on the positive interval from 0 to x. You only take that function supported by q to the kx. So support that function, that is q to the k should be delta in that point. No, this means that is delta in that point, like geometrical progression. That function was known as a Jackson integral or maybe some other that was discovered many, many years ago. For all real line, you can do positive and negative. And what is nice also that for type 1, discrete Hermite polynomial, orthogonalized measure, or q-Gauss, discrete q-Gauss I call, in opposite to continuous when I start with q relation. This is just a discrete measure. Of course, when q tends to 1, you obtain classical. But it's interesting when q tends to 0, this has a sense, and that you obtain just 2-point measure, and this is in non-commutative probability is called Boolean probability. Maybe I don't say more about this, but you can find about this in many references on that subject. So this is like interpolation between Boolean and classical probability, and we expect that is nice, much nicer, because explicitly formula. Maybe I give you more formulas. So I wrote the commutation relation. So as I said, I take in the general, when it had 2 parameters q and s, I put s equal q and q without replacing, and we have the creation new one and qq, annihilation, and position operator g hat. And that kind of this weak formula, the generalized moment formula, when f1, f2, n are element of Hilbert space, appears, of course, correlation between fi of j. So, and that function is 1/2 inner point plus crossing. And here you see that is connection between that function. And I wrote to you before, there is some connection between inner point crossing and nesting. So it's some relation between this. So this is combinatorics, and I hope that people which like combinatorics will be fine. And we come to that combinatorics through commutation relation in q-discrete Gauss. Also, you can take measure corresponding probability measure in 1 dimension. So that function moment, only even because measure is symmetric, is like classical moment of Gauss, 1 times 3 times 2n minus 1, but here is the q numbers. And that is also at q to the e0 v when v is partition. And that function is just 1/2 inner point plus crossing. And that function is 2 bracing plus 2 crossing. And that function was discovered by De Medicis is Viennot, maybe 20, 30 years ago, from combinatorics in different contexts. So I'm happy that we come through physical problems to that same combinatorics. How is my time? I should be careful because I understand 45 minutes and some minutes for discussion. Yeah. But if I have something speaking too much, I have Blackboard. I can really, as you know me, I like Blackboard, but here it's not so easy to work with computer and Blackboard for me. Okay. So here I wrote explicitly for q-discrete Gauss, q, the relation is, because we replace s by q, so it will be a q f a star g minus q squared, and that we change. and that q to the number operator. That relation, somebody said me, in one dimension was discovered by some mathematical physicists for special degenerate or extension of q oscillator. When this is connected with quantum groups, special quantum groups. I've forgotten the authors, but you can find this. Yeah. So now, main problem, what I say for my talk, which is I couldn't solve, only partial result. I claim that we have positivity result for q-discrete and also continuous is also q-continuous Hermite and q-Gaussian convolution, we define it, but prove positivity. So when you have two positive measure, probability measure, you define by that formula cumulant, because moment cumulant is that formula, what we call weak formula, and prove positivity. For some cases, we know, but q0, q1, or this is very special, but other, although we have discrete Poisson and q-discrete, I don't see any paper, any result in this. Also, I see later for show you when I calculate Khintchine inequality, we would like have no explicitly norm because that operator are bounded. So we would like see the norm, operator norm of that Gaussian. And also is open problem for which Q this faithful state vacuum is faithful state. Because this is faithful state, this is that we are very glad and happy and we can do more. Okay, so this is, I hope that after that conference, we obtain soon from young people result that is okay. Now I have some digression, because I have 10, no, yes, sometimes I can say. So there are many, also another convolution, but not connection with so much with the, let's say, mathematical physics, more with this was done by Koornwinder and his co-authors, students. And for example, they defined some ersatz, some extension of Jackson Q moments for rather good function when you use just Jackson measure dq of x. And also here is for convenience, for some the technical reason, some dilation q to n over 2. And Carnovole and Coornwinder, they define analog of q-convolution of two function, like should be just by moment formula, using that kind of q derivation. The q is the q derivation is like fx minus fqx divided with x minus qx. And the limit, of course, at 0 is derivation. And of course, also they don't prove positive, but they prove at least associativity. But of course, from here is not so easy to see. And we have some analog like convolution when q equal 1. So you have just, you can see that that formula gives you convolution f times g classical convolution for q equal 1. Also, Carnovole and Coornwinder for good function prove that the q-discrete is associative and commutative. It's not so easy because moment is using that Gauss symbol, deformed n over jq. Anyway, in the q equals 0, we have Boolean convolution, q equal 1, we have classical. So will be interesting, I wrote problem, find characterization of q-discrete moment sequence, because for classical moment sequence, when q equal 1, this is just a lot of characterization, moment sequence, just as a positive defined Hankel matrix. Also, there is a corresponding Cauchy transform, but here should be some deformation of that notion, and we don't know. So problem find characterization of q-discrete moment sequence for that situation. Even more, people consider braided line. So braided line is just algebra of formal power series in variable x when just braiding is just changing KL, but also Q to the KL. So usually we have braiding just exchanges X to K, X to L, but here appears a parameter, and also co-multiplication, which is natural. Of course, with q-Gauss, antipode, braided antipode, and we have Taylor formula, q-analogue, so we can, and that is related to our business. Yeah. So, and later on, Kem and Majid found that is related to very special quantum group when you use q dilation in argument. Yeah. I don't come to details, but we have that appears here exponential function that small aq, that delta, that is co-multiplication like should be, and inverse, but inverse as co-inverse replace small exponential, sorry, a small exponential function to big EQ. Yeah. So you see this, some problem is that we have two exponential and how to do with this for mathematician is. Okay, so now I have to the main topics of my talk. That means q-discrete Brownian, q-discrete Fock space, q-discrete of type 1. I don't say detail before, but now maybe more details. So for q, we consider parameter q between 0 and 1, and we define q-discrete Fock space, which for q-1 is just classical, but q0 is free Fock space. And that is just done like this, that we have just for tensor x1, xn, y1, ym, that should be orthogonal for n equal different from n, but here appears could do the inverse of pi when pi is permutation. So this is our what we define it with Speicher q Fock space. And annihilation is just occretion is just left multiplication by tensoring f by tensor cn. But annihilation is like q derivation. And for one dimension is really derivation, and that is just, but here we change because we come to the discrete. So classical was without, we don't put here q in the between some q to and q to n minus 1. But here we change of annihilation operator, and this is another kind of q derivation. When we annihilation on tensor x1, x here is misspelled, q should be finished xn is equal q to the n minus 1, and here is q derivation. And such a operator on the full Fock space, but with new scalar product, which here is done, yeah, is just creation is conjugate to annihilation and vice versa, and that satisfies that relation. Yeah, what here's q commutation relation AF A plus G minus Q squared H G AF Q. By the way, this is very close to our paper we done maybe good 10 years ago with Professor Yoshida from Tokyo University, that we put here that parameter S even not Q. So here is like S Q is equal S squared. It's also some another construction which comes from another reason, from another deformation. So this is our q-discrete commutation relation. And of course, everybody would like know, of course, this is bounded operator. This is different from the, for q, of course, less than 1. For q0 is the Boolean, but so I recall that we just defined it q-discrete Gaussian random variable as a position operator, AQF plus AQ plus. And I repeat, we have again weak formula, q version, for discrete version, when here appears the function inner point and crossing for two partition. And our Gauss at vacuum state, omega, has a spectral measure, which is explicitly you can wrote. I wrote on beginning of that, But for us, it's more important, not explicit measure, but orthogonal polynomial. And the orthogonal polynomial are just q-discrete Hermite. I don't know if the Hermite, when he considered Hermite polynomials, thinks about such a deformation. Anyway, but we have such a deformation. So we have x hn equal hn plus 1 plus q to the power n minus 1 and q numbers. Yeah, so and q quantum numbers is then. And that in literature appears, and that among combinatorics usually. But here is sometimes it's better considered discrete. That appears theta function, but here is some function which is corresponding to theta function of, or not theta, to Jackson integral, and an exponential function that capital E of Q. Yeah. Of course, and now for us it's important also we have Brownian motion, and that construction is very general. So we would like to have also q-discrete Brownian motion, and we are doing like this, that we take Hilbert space, a real line with measure, Lebesgue measure, positive real line, and we take characteristic function f interval 0t, and then we define it Brownian motion q-discrete as our q-discrete Gaussian with respect with argument that characteristic function. This, of course, this is corresponding to the physics interpretation that Gauss should be integral from 0t, just creation and infinite creation and infinite annihilation. Yeah. And for Q is the classical Brownian motion, for Q equals 0 is the Boolean Brownian motion. Unfortunately, they are quantum, so they are not commuting. So the problem is that is for Q1 is commuting, for Q0 is Boolean is very non-commuting. Also here is some version, but nevertheless we have nice result, and I maybe just before coming to next, we have yet some minutes, I think at least 5, so I only say the problem which we study with many people in Wrocław with Professor Speicher and other, Kummerer, and also Jung and other Japanese people. We consider for Neumann algebra generated by Brownian motion. And of course, trace here is not, of course, you can check it, that trace is not vacuum expectation is not trace. So that should be, we expected that it will be kind of factorial for Neumann algebra. This is like weak operator closure, but we should prove that this has not center, and that is not yet done. And that should be, as I wrote, the algebra description of type 1, and that for the Q continuous, we prove this is factor 2, 1. But here I expected will be type 3, and the Q should be corresponding to the Alan Kohn characterization of factor of type 3, but not yet done everything. But I am almost sure that should be natural construction here of type 3 factors. I think that Gerard is preparing to stop me. Not yet. I have a few minutes. Yeah. 5 minutes. Okay. Thank you.
5 minutes to 45, not to 50. So
okay. To 45. Yeah. So I have more. Even. Okay. So as I said, for the continuous Hermite for Neumann algebra, is this 2-1 factor. We proved this by Kummerer with Speicher some years ago, and then for finitely many was done by Eric Ricard from Besançon, but now is professor in I've forgotten the Rennes in the north of the France, and he proved everything. There are 2-1 factors, but here corresponding, I think, type 3 factors. Okay, and now which sound change with my list? Okay, so now is last 5 minutes. Let's say if chairman agree, I would like to show why that new Gaussian are important in at least mathematics, and I hope also mathematical physics, because for that Gaussian, q-Discrete and some other, which I don't define it, q-Gaussian and a q-continuous, is such that we have following matricial version. Yeah, Gerard, there is some question, problem? Is okay? So we look for Khintchine inequality, so but very special one, that we have random variable x1, xn, and which is bounded, like Rademacher, for example, that means corresponding to Bernoulli, and that norm of this operator knows of maximum is equivalent to maximum a j. If it is scalar, this is just aj square. But here there are matrices, so we have like two norms. We don't, because the matrix is not commute, so we have a star norm and a star a. That so-called row and columns operator spaces was discovered by many people. Mostly was done by Professor Pizier, Rouen, Efros. They work on that business some times ago. And we also discovered Professor Leinert, which was working on that subject also on free group. And theorem, what we have, maybe that if we consider q-continuous or q-discrete Gaussian, and maybe Gaussian, Kesten, this corresponding to free group, I don't define it, but this also corresponding to some parameter which I don't define it in my talk, that inequality or equivalent, because inequality is both sides, yeah. That means that operator is bigger and less, like in Khintchine inequality, usually, and that they are just satisfy all this property. Of course, that constant depend on parameters, but for Boolean case, when is the special, we prove with Krystek and Łukasz Wojakowski that this is equality. So the Boolean, so corresponding q-discrete for q0 is very special, that in that row columns Khintchine equality, we have equality. So for every, and that equality is for every matrix is aj. So not complex, yeah, there's any complex matrices, so you can get even to operators. Yeah, and this is operator norm. If you use some interpolation, you obtain Schatten norm, that trace of matrix A to power P and that P norm, 1 over P norm. By the way, Schatten was student of Banach, was Polish mathematician from Lwów. Now he's in Ukraine, and he did a lot of, everybody maybe know him from other business, from tensor. He was connected with also von Neumann. Okay, so what I have, and corollary is that if we prove this with Kummerer and Speicher in special case, and later other people, that if that von Neumann algebra generated, but such a random variable would satisfy that Khintchine inequality, has a trace that von Neumann is not injective and also is a factor. So factor is that important, and this was important to prove in factoriality. So I hope that here we also can do this, and that will be, I hope next year will be conference when some result. So that paper is with my son, which is professor of Technical University in Wrocław, and I am in his office. So he is now working on quantum computing, and this is also related to this. I think this is all what I would like to say. Of course, I should put references, but I'm sorry I forgotten to put on the slides. So I thanks once more to Professor Gerard and Professor Karol for inviting me, for other professor, Professor Koncewicz and other committee, that I am among you, and I have thought even I couldn't be personally in such a beautiful place like Isches. Merci beaucoup.
Merci beaucoup. Now we have time for questions. Yes, Carol.
I have a question.
Yeah.
have chosen some versions of deformation of commutation relation, and then you have shown then that there is a equivalent of Laplace convolution
Yeah.
in this case. And I would like to know whether it's possible to define equivalent of multiplicative convolution of type of Mellin, not of type of Laplace as you did, but multiplicative. This
Uh,
would relate to the
Thank you for question. We think because this is Mellin transform, what you like also, and this is connection with, is that Fourier or Laplace or we don't yet done, but I hope that if it will be interest of you, and we can do this, and we wait for only some time, and we inform you more. But if you send to me more detail of your question, maybe some papers or your, so I understand that will be interesting to extend to multiplicative version. But like in free case, also there is a not only additive, because I said here about additive convolution. Yeah, you are thinking about like multiplicative convolution, and in classical this is Mellin transform, but also in free case also there is such a notion. This corresponding Voiculescu S transform. And I hope that here is some kind of interpolation between 0 and 1. When parameter 0 is the free, q is 0 is when q is 1 is classical. So I hope that is big chance. First, we should do probably do this for the continuous, because maybe it's easier, but maybe discrete. I don't know. But thank you for that interesting question and problem. We will be thinking about this, and I hope we are soon give you some concrete answer. Merci beaucoup.
Thank you.
Other questions? I have a small question about slide 16.
16. Let's say so. Where is this? Because I have one here. That one. So the facts about that function. Yeah.
Berger q exponential, because it's
formulas. Yeah.
With eq of z, eq of minus z equals 1. And,
that is the classical formula, but you should small and big. So you have, as I wrote here, small aq is this, but capital is using q to the another 2, yeah? And that formula is like this. So this other, and anyway, I like the first formula because that say you what is 0, but when it's 1 over, you have even what is problem. So that function is most natural than exponential, yeah. Yeah. Anyway, but this is that situation, yeah. Anyway.
Question. And I have another one on slide 21.
31.
You took the q-Jackson q derivative.
This one, that one.
21.
20, sorry, 21, yeah. Oh, that, okay. So this is convolution of Carnovole and Coornwinder.
Yes.
Jackson, yeah.
Deform Leibniz identity such that the scheme of action of delta q is, you call it delta, capital delta, is delta tensor 1, means that if you attack a product, you attack f and multiply by g, plus a character, it is f of qx multiplied by delta of g. It has a sort of Leibniz. It is, well, okay.
Yeah,
but
so
maybe you don't use it, you know. Okay.
No, at least I don't know, but thank you for your your suggestion and looking for this. We will be looking more. Of course, this is done by our colleague in Institute, Ania Kula, which she working on that more. But still, we don't see at once the commutation relation. Also, Coornwinder, which follows some like braided, not classical quantum group. So this is when we look more, that not this one, maybe here is, so connected with not quantum group, but braided quantum group or braided algebra. So some generalization of yeah. Thank you anyway for your question, and we should be more careful on that, your suggestion.
We thank the speaker again, unless there were some other questions. Okay.
So merci beaucoup.